can Opava and do it in person. Very close to my heart. Know the streets of Opava. Okay, so I'm going to talk about a mixed bag of two things actually. One is global GRMHD models, where I'm trying to address one major problem in accretion disk physics, which is about what's the fate of radiation pressure dominated innermost region of Shakros in inner disk. Okay, so this is a bit of outline, a bit of history or introduction about accretion disks. What are the major problems in my opinion, and what are the tools I'm using for solving those problems? And the variability part, which is about a symphony of these black hole accretion disks. So I know that you guys are expert on these QPO features of these different accretion disks around black holes. And that's also very interesting for understanding the properties of black holes. So I call it black hole symphony because they are in such a harmony in terms of frequencies and their values and ratios. So we all know that now the black holes are confirmed, like they do exist in nature. This was the very first observations when you find that there are stars going very rapidly close to the galactic center, and they were not behaving normally, like in elliptical orbits, but they should have been expected. You see the yellow trajectory here is going very close to the central part and then rapidly getting a speed up star and then returning back. So people were speculating, and eventually this was the discovery that it's a supermassive black hole at the center of our own galaxy. Now, the second confirmation is just a very recent one from Event Horizon Telescope collaboration that we are getting every other year or few months, we are getting something really exciting from this collaboration, Event Horizon Telescope collaboration. So on the upper left corner, what you are seeing is a GRMHD simulation, ray traced and creating that image. So that's not the observed one. And the lower left is also like a rendered global general relativistic magneto-hydrodynamical model. On the upper right corner, what you are seeing is the most famous picture you have been seeing in the news and articles and research papers from EHT collaboration. So this is the first image of black hole M87. How to get that? It's pretty complicated. You do probably 100 or 60,000 GRMHD images and then just compare them with observations one-on-one and just keep following that process until you get the best fit and template fit for the GRMHD simulations, and you find this picture. So this was an effort of probably 800 people from across the world to come up with this picture of first picture of a black hole. So this opened up a really new whole area of research for at least next 20 years or even more to understand the accretion disk more precisely, very close to the black holes. Now, how do black holes actually swallow a star? So there are different scenarios, like there are different systems. The very first picture I was showing, when there is a very supermassive galactic center black hole, and then there are stars orbiting around it, and they produce winds, and they feed the accretion disk around supermassive black holes. But there are two other scenarios where there is a system in a binary. So you have a accreting black hole, and then there is a companion star, which is actually going to overflow because of the pull or the strong gravity of the black hole, and that's called Roche-Loeb overflow. And it starts to form an accretion disk in this so-called black hole X-ray binary system. The other interesting scenario, I want it to be here. Yeah, so the other interesting scenario is this one on the left part here. So that's called tidal disruption event of a star around a black hole. So this is the model we did for a different purpose. Actually, we were trying to understand intermediate mass black holes. But the idea is that if a star comes too close to a black hole in a parabolic or elliptical orbit, and it crosses a certain limit and gets too close to the black hole, it will be tidally disrupted. So that's more because of tidal forces acting to disrupt this star. So that's another interesting area of research, and it's developing very rapidly because we are getting more and more observations of tidal disruption events. So a bit of background, like where do we see accretion disks? They are actually everywhere in the universe. You have supermassive black holes, they have accretion disks around them. Smaller stellar mass black holes, they have accretion disks. Protoplanetary disks have accretion disks. Neutron stars, and the galaxy itself is like a disk structure. So it's very important to understand the physics of these accretion disks to understand different scale problems in the universe. So a bit of history, probably not going back before the standard disk model, because certainly the accretion physics was proposed much earlier, probably 1960s, but I'm starting from Shakura-Sinai model when the things started to get more organized and coming up with the observational evidences for explaining the observations from their models. So the one I'm going to talk mostly today is geometrically thin disks, which are proposed by Shakura and Sinai from 1973, the most famous paper you guys know. The other model is from Marek Abramovich and a group in Warsaw. Those are called thick accretion disks. So these are two different models, and primarily I am working on geometrically thin disks and a bit on geometrically thick disks. So comparing observational outcomes from this kind of sources. So these are the most powerful luminous sources in the universe. Like if you compare it with the nuclear burning, like you burn a certain mass of radioactive element, and how much energy will you convert from that? That's like, say, rest mass energy of like, say, 0.007 mc square. If you have a mass of m and you create some kind of nuclear reaction and produce some energy, that energy gain is just 0.007 mc square. Now, if you take that same mass and throw it into some star, or say neutron star, or any star which is accreting this mass with a radius of 10 kilometer, and the energy gain is like 0.1 mc square. So you see how much energy one can gain just by the gravity, which is so strong for this kind of sources. So most luminous sources in the universe, and probably easier to observe for certain sources. Now the important questions are like how these plasma falls into the black hole in the very vicinity of the black hole. And once we understand that, we can infer some properties of black holes, and say, let's say, based on timing variability from these accreting sources like X-ray observations. The most important point in next 5 to 10 years will be confronting your simulations or our simulations with observations, which is happening more and more frequently now, that GRMHD simulations are being confronted with EHD observations. I just hope that someday we'll have a long enough well-resolved simulation that we can compare that with, say, variability and the spectral state transitions in black hole X-ray binaries. So those are the key future aspects that we want to confront these simulations with observations and not just run on supercomputers and try to infer some models. How do these accretion disks look like in numerical models? So what you are seeing here is a two-dimensional sheet of different profiles of accretion disks. So the one on the very left side, that's called geometrically thick disk, because you have a torus kind of a structure, and what you are seeing is just a RG slice. And at any given radius, the ratio of the height to the radial location is approximately 1. And then there are thin disks, which are at any given radius, the height to radial disk location ratio is way much smaller than 1. It could be 0.05 or it could be 0.1. And then there's a different class, which is slim disks. And those are advection-dominated accretion flows, which fall into a high temperature, higher mass accretion rate disk regions. So why do we need to do simulations with magnetic field? The reason is that if you don't seed any magnetic field and you leave a disk around a black hole, what you are seeing on the right-hand side is called pathological instability. So if you don't seed any magnetic fields, your simulation should remain stable and it should not be accreting until unless you have some initial perturbation to break the stability. So that's the right-hand side. Then we perturb it, then only it happens to show up this pathological instability. But on the left-hand side, what you are seeing is a torus. It's a 2D model just for illustration, because we cannot rely on a 2D model to keep running the simulation for a long time for certain different regions of magnetorotational instability and maintaining the poloidal flux. And what you are seeing that if you seed a torus with some magnetic field, it starts to accrete onto the black hole and form an accretion disk. So we definitely need magnetic field to solve these problems. So I'm more going to spend a big chunk of time from this talk about trying to understand the spectral state transitions at some point from these global numerical simulations. So we know that when you observe certain black hole X-ray binary systems, they follow this hysteresis profile, which is on the right-hand side here. That's also called Q diagram, or there are so many names for this. But the whole idea is that any given system spends time on different states, A, B, C, and D, at different times in their accretion disk evolution. So it spends mostly its time at state A, which is quiescent state. Then it starts to increase its luminosity, but maintains the X-ray hardness, which is on the horizontal axis. And it keeps increasing the luminosity and goes to state B. And then it starts to move towards a softer X-ray state, which is more going towards state C. But when that's happening, if you see this jet profile there, there's a part when the jet shuts off. So that's interesting. Like you take a binary system, black hole X-ray binary system, more precisely probably low mass black hole X-ray binary system, and you keep watching it, that how it evolves with time. So at certain state, you were seeing, okay, there is a disk and then there is a jet, everything is working fine. But suddenly you notice that, okay, the jet has shut off and you don't see any jet. And the disk is started to become more towards geometrically thin disk, not remaining a geometrically thick disk, or something also we call radiatively inefficient accretion flow. So then you go to softer state, and then this system keeps repeating that. The big problem that numerical simulations are facing, that it's very hard to simulate this entire cycle in any global numerical simulation, because what we are simulating is barely a few seconds or a few minute time, and these things are happening at few days to few months or weeks time scale. So we have to invent some way of tricking numerical simulations, like having very close to transition region. That's what I've been working for last 3 or 4 years, trying to set up a transition and seeing how the disk spectral state changes. And just to rate, probably there or those who do this kind of simulations might disagree on that. So my understanding is that setting up these models had certain challenges. So that's how I rated it out of 10, that what physics you include and how challenging is that. So most technical part is actually including the radiation physics. It's not general relativity, not MHD, not switching from local to global models, but it's more about radiation physics. Why is it more costly? Because it's numerical challenge is more about computational cost, actually, that you cannot run a model with many photon frequencies and then try to generate the spectrum. Recently, there has been some development to minimize that cost and yet do multi-frequency radiation models, but still, if you add the radiation, the cost of simulation goes up really quick. And when we did this kind of simulations with high resolution grid, typically it's costing about 10 million CPU hours for one simulation. So these are the challenges that you face when you try to set up some global models with radiation physics. And the motivation is a bit based on this not hypothetical, but more like a speculative idea of Mitch Begelman and Phil Armitage. So, sorry, what they are trying to advocate, that if you have an accretion disk, which is say on the lowest right corner here, the flux accumulation part, where so you have a geometrically thick disk with a transition radius where you see this magnetic field loop, and then a geometrically thin disk. So what Mitch is advocating, that the inner part, which is geometrically thick, is prone to advect the magnetic field as well as radiation into the black hole. So it will efficiently advect the magnetic field and try to accumulate more and more magnetic field. Now the transition region might have a fortunate or unfortunate situation that it's a loop which is going to be advected in geometrically thick flow, because they tend to advect the flux, and geometrically thin disks, on the other hand, tend to diffuse the magnetic field. So this loop will start to separate out and try to accumulate more and more field in this inner part. So what he's trying to say, there will be accumulation of magnetic field in the inner part, and that could lead to a transition from, say, soft state to, or say, quiescence to hard state, high luminosity hard state. That will be somewhere before the jet line. And that also advocates that how you can produce jet in these regions, but when you make a transition from the advective flows to a geometrically thin disk, you don't have jets, because you don't have enough magnetic field or enough large scale poloidal field to launch the jet. And that has been more clear in recent EHT observations. And I think they are writing a paper that you need some kind of large scale poloidal flux to produce these jets. So now the models I was doing to understand the problem of like radiation pressure dominated disks, which are thermally unstable. You all know that what happens if you have very inner part of accretion disk and which is radiation pressure dominated. It has been found theoretically that it's thermally unstable. Now, if you compare that with different local shearing box simulations, there was a bit of debate for at least 7 years that these radiation pressure dominated disks are thermally stable. That was one paper. And then there was another local shearing box simulation which came up saying that no, disks are thermally unstable. So this was the first time we tried a global model to conclude the debate and check the final fate of these radiation pressure dominated disks in a fully global model. So what we did, we set up a geometrically thin disk in cylindrical polar coordinate system with GR included and also the radiation included for a geometrically thin disk. So these are the boundary conditions that we used: outflow boundary conditions for above and below the simulation domain, and outflow very close to the inner, like close to the black hole, because everything leaving the inner boundary is going to fall into the black hole. Since these were already very costly simulations, we did just 90 degree in phi. We didn't do a whole 360 degree. So it's a periodic boundary condition. The outer boundary condition is constant because that's more realistic. Like you are constantly feeding some matter from the outer boundary to supply the disk some material to constantly accrete onto the black hole. And a bit of technical details that we did actually 4 simulations to confirm that what we are seeing is not just artifact of numerical simulation, that the disk is thermally collapsing. And we did a gas pressure dominated simulation to confirm that, okay, the gas pressure dominated disks are thermally stable and the radiation pressure dominated disks are thermally unstable. Different resolutions were just again to check that whether having lower resolution is affecting the outcome of these results. Like if you have very small resolution in certain direction, you are not able to resolve those MRI modes, magnetorotational instability modes, and you might not supply enough heat to keep the disk puffy or elevated. So we did 2 resolutions in 5 directions because our parameter which defines the criteria for magnetorotational instability resolution was much lower in the case of first run, which is 32 grid cells in the 5 directions. So eventually we found that it's thermally unstable and it's collapsing. So this is an animation from that simulation that you see the initial stages, the disk was getting thicker and eventually it collapses to a single cell, which is not resolvable anymore. There are some speculations that if we have high enough resolution and we keep running this model, it might come back to, again, a normal disk structure, but that's just speculation and we cannot resolve that at the moment. But while doing these geometrically thin radiation pressure dominated disks, there is a philosophical problem to initialize them. You probably are familiar with the stability curve of accretion disks. So you have, on the vertical axis, you have temperature, and the horizontal axis, you have surface density. And if you pick a radius in accretion disk and pick some value for the viscosity parameter alpha, you get these branches of stable solutions for accretion disk. Now, the problem is that the GRMHD models need to be initialized with some alpha value to have your model somewhere either in let's say I'm simulating a radiation pressure dominated disk, so it should be somewhere on the horizontal branch, which is radiation pressure dominated branch. So now T0 should have been on the unstable horizontal branch. But after doing the GRMHD simulation, we find that, okay, the alpha was not what we expected, because a priori you cannot predict what alpha will be for a global model. So that's why when we got the simulation done and we got the alpha value from this simulation and plotted the stability curve, we were off from horizontal branch and slightly below from where we started our simulation. So the T0 here is the initial state, and then it keeps collapsing towards a stable branch. So this was a challenge for a big global model. So we studied it again with the 2D hydro models to have a detailed study that how to exactly initialize it and where to initialize it and what happens depending on where you initialize the model. So from those global GRMHD simulations, what I'm trying to show here is a plot for ratio of heating rate to the cooling rate, which is shown on the color bar here. And the horizontal axis is again cylindrical radius, and the vertical axis is time in geometrical units. So the left-hand side plot is actually gas pressure dominated simulation of Shakura-Sine model, thin disk model. What you are seeing here that it's mostly around 0 for this log Q plus over Q minus. So this was a thermally stable disk. But on the right-hand side, if you see the ratio of heating rate to the cooling rate, it's dominated by the cooling rate. So the disk was collapsing as the cooling rate started to dominate over the heating rate. Since we did it for the first time with general relativistic effects, we also know that the viscous instability, the time scale for developing viscous instability reduces when you add the GR effects. That's from papers by Bojana Cherny and Rafal Madrusky. So we noticed that in the very inner part, we are seeing the ring structures in these simulations. One thing to clarify, these simulations are not entirely 3D. So this is just to illustrate this viscous instability ring and replicating that 90 degree for 360 degree, just for illustration purpose. This simulation is not 360 degree. So what we noticed, a very clear structure of rings in the very inner part. And when we tried to confirm what could it be actually, the time scale was matching for viscous instability, and the anti-correlation of stress and surface density also matches to say that this is viscous instability. It has not been reproduced yet, so this is first finding, and we need to do more simulations to confirm that and make sure that this was not any artifact. So that's what viscous instability showed up. But as I was mentioning, that the philosophical problem of initializing a geometrically thin disk for a GRMHD model was challenging to do many 3D GRMHD simulations. So we turned off magnetic field and started to use alpha viscosity for these simulations and just do 2D simulations because we wanted to do as many simulations as possible. So on these two panels, what you are seeing is at two different radii, that how the initial stages evolve for the different simulations. So no matter where you start your simulations, it always falls onto the stable branch, which is the lower branch here, the gas pressure dominated branch. The biggest debate was that if you start above the horizontal branch, it should evaporate and go towards those slim disks and find an upper branch solution which has been mostly advocated. But if you see those cyan colored triangles, they are again following that trend and falling down. So even if we start from above the horizontal branch, still it falls onto the stable branch, lower stable branch. So that concluded that the disk does not show evaporating structure. They mostly collapse to a lower gas pressure dominated branch, no matter where we initialize it. But in nature, these disks do not show this kind of thermal instability. They sustain there for many, many millions of years or even more actually. So they should not be showing this kind of instability, which cannot occur in the nature. But when I'm saying this kind of instability, I mean in black hole accretion disks. So then our previous groups, Oleg Sadowski and Deborah did this work in 2019. And Mitch also advocated this in 2015, that what could stabilize these radiation pressure dominated, thermally unstable Shakra-Sinai disks. So we think that the magnetic fields can help to sustain this thermal collapse of the accretion disk by providing enough magnetic pressure support to not let it collapse. So these are three different regimes of magnetized disks. One is weakly magnetized disks on the left side, and then the region I'm interested in strongly magnetized disks, and then the last one is magnetically arrested disks. Those are one more towards what EHT group is trying to simulate, and those are completely different from what we are trying to understand. So these simulations are, again, as I mentioned, they are very expensive. So we wanted to reduce the cost by putting the static mesh refinement for these simulations. So the other thing also I did was turned off general relativity to reduce the computational cost and do entire 3D model with highest resolution we can. So we added three different refinement levels on top of the base grid of this simulation. So these simulations are done with code Athena++, which has the static mesh refinement and also adaptive mesh refinement. So we were able to set up this model with a grid resolution of 2048 times 512 times 1024. So this was a really high resolution for a global MHD model. But then we started to find something more interesting, which I'm probably not going to cover in this talk, but maybe in some other talk, the spiral structures. However, the idea is that when you seed the accretion disk with three different beta profiles, so beta here is ratio of gas to magnetic pressure. So that tells you how strongly or weakly magnetized your accretion disks are. So I tried a beta of 1000 and then 3150. So 50 will be the most strongly magnetized case. And in all these simulations, what we are finding is that the disk starts to accrete onto the black hole. And not only that, it shows something very intriguing and interesting. So that's what I think Deborah coined the name puffy disks, and we wrote the papers probably in the same time frame, and we called it elevated disks. But the qualitative picture is same for these two different accretion disk models. So on the left-hand side, what you are seeing is an azimuthally averaged slice of density on the left half and the velocity on the right half with the magnetic field streamlines on top of them. So the most surprising thing was that the accretion on the right half panel, you see, the accretion is not happening at the midplane. It's primarily happening on the surface of accretion disk where the magnetic field is pinching in. And this only happened when you seed the accretion disk with vertical magnetic field. So these simulations are seeded with a purely vertical magnetic field at time 0. And as the simulation evolves, this surface accretion starts to happen. They are pushing the magnetic field inwards and creating this pinching effect. But the mid plane is actually showing weak outflows, which is very interesting that you see that magnetic fields are bending outwards, and also the velocity component here is positive. So the negative component meaning it's accreting in, and positive is pointing outwards. And together with that, when you initialize these models with some beta, let's say 1,300 or 100, in the surface accreting region, you end up with much lower beta. So like the region where the accretion is happening is around 0.2 or 0.3, and the beta, let's say if I start from beta 100, it's going around 0.01. So it changes significantly, and the disk gets strongly magnetized, and the toroidal component of magnetic field starts to dominate. When I say why the disk gets magnetized, like strongly magnetized, when we seed it with the net vertical magnetic field, it's again because of the interesting feature of differential rotation of accretion disks. You take a vertical magnetic field loop and you drag it in the phi direction, but also drag it radially inwards, and that's producing a large radial component. And when you have a large radial component, you tend to azimuthally drag it and produce more and more toroidal magnetic field. So if I keep running this simulation, it keeps producing large toroidal field and supports the disk and keeps it elevated at accretion happening around H over R of around 0.2 or 0.3, which is different from Shakurasina model, where the accretion is happening probably at the midplane, and also the disks are much thinner. So that's why we started to call it elevated disks, and also Deborah calls it puffy disks. Now, when we did that Newtonian simulation, we wanted to reduce the computational cost and just study the magnetic effects and see how it elevates or puffs up the disk. Now we have started a series of simulations where we added GR, and then we added radiation, and now also vertical magnetic field to see how this puffiness maintains, and does it really help to suppress the radiation pressure dominated Shakurasina thermal instability. This has been shown by Oleg Sadowski in his 2016 paper, but we wanted to do it with net vertical magnetic field, unlike Oleg did for quadrupolar magnetic field configuration. This is a second part of my talk. So if you have any questions for this part of the talk, you can ask now, or I can keep going. Okay, so if no questions, then I'll quickly go to the more interesting physics from these black hole X-ray binaries, or generally the variability. So when I call it harmony, because when we observe these features, they are at some fixed frequency ratio. Sometimes they are harmonic, sometimes there are some overtones and some different ratios of frequency, even 1.5, or even more interesting, like say 5/3. So these are observed in nature also. When you talk about black hole accretion disks and quasi-periodic oscillations observed from these black hole accreting systems in the X-ray observations. So I spent a big chunk of time on studying this time variability from these global models and understanding what happens when you create some kind of perturbations onto the accreting matters. So this is a very interesting simulation that we did in 2016 and 17. So you have a small blob, or you say a torus cross section set up around a black hole. The black hole is at the center of this coordinate system here, and I'm putting this torus, which is again geometrically thick disk model I was talking about, but in 2D, and then perturb it. Now, if you keep watching it for a long time, you will notice that it's actually breathing, and you can just look at the time here and convert it into frequencies, and you will find that at this particular radius, this corresponds to breathing oscillation frequency. And that led us to more and more interesting findings from this simulation. And the one interesting thing was, if you take the same model and try to change the size of this torus around this black hole, like cross-sectional radius, how it follows a fixed ratio for radial oscillation frequency, and also something called plus mode oscillation frequency. So these kind of accretion disk models have been studied by Omar Blaise and a lot by you guys in Czech Republic, that different modes exist in that, and that's called plus mode, X mode, radial mode, and X mode. So these different modes exist in these models, but I'm showing here is the plus mode and radial mode frequencies, which are maintaining an approximate 3:2 frequency ratio. So that was exciting, because 3:2 frequency ratio is often, I wouldn't say often, but observed in some sources, and not very clear what could be the source of that. So that was interesting part, that something like this could be happening, and that could explain that observational feature. But then I did this series of geometrically thin disk simulations, and there also I find this 3:2 frequency ratio. So what you are seeing here is power density spectra of vertical component of velocity at the midplane, and the horizontal axis is showing time. So these peaks actually in the blue curve, it's actually at 3:2 frequency ratio. So this model is not a torus model. I was just showing this breathing oscillation, but actually a geometrically thin disk, and still showing those 3:2 frequency ratios. Then we kept investigating that with Vlodek, and we found a whole treasure of oscillations in these models. You see there is so these plots are showing different frequencies. So the upper left panel, the blue curve here is radial epicyclic frequency, and this white dashed curve is vertical epicyclic frequency. So these black holes, these models on the upper left corner is actually non-rotating black hole. And if I take a single radius, or say a few different radii, it matches with the discoseismic G mode frequency at that particular radius. So that peak I'm showing on the upper right corner plot is actually at this fixed frequency of 3.5 that corresponds to discoseismic mode frequency at this radius. And then we did a bunch of more simulations to understand the effect of black hole spin. So on the lower right corner, you see that the same G mode frequency has shifted a bit down as expected from a spinning black hole of 0.5. So to summarize too many plots here, if you take a non-rotating black hole and a geometrically thin disk around it, and calculate the variability or compute the variability from these simulations, and then change the black hole spin, all the frequencies shift accordingly for that given black hole spin. And then we find also breathing oscillation frequencies, and like this 5/3 for vertical epicyclic frequency. So this was a wealth of different oscillation frequencies in these global models. But the most interesting phenomena we noticed is on this upper right corner plot. At radius of 10.8, you see these two bright spots. And that's what Marek and Glodek has been talking about, this resonant oscillation model for 3:2 frequency ratio. So this is at 10.8 for a black hole spin of 0. And that ratio comes out precisely 3:2. And that's expected for this particular radius. And on the lower part here, what I'm showing is something not in agreement actually with Marek's and Glodek's model, is that when Marek and Glodek proposed this model, they suggested that at radial epicyclic frequency, the oscillations should be happening radially. And at vertical epicyclic frequency power, the oscillations should have been vertical. But if you see the eigenfunctions of these two frequencies on the lower two plots here, actually in both cases, the fluid is oscillating vertically up and down. So these eigenfunctions are showing, I picked these two frequencies, upper and lower frequencies, and compared how the fluid should be moving in space. And what I'm seeing is it's vertically moving up and down at these both frequencies. So, sorry. So then we are not certain about concluding Marek's and Glodek's model just from these two plots and simulations. But this frequency ratio of 3:2 is getting prominent in most of the simulations I'm doing. Now, recently, I also jumped into like more interesting physics, where I'm looking for more students actually who are interested to do this kind of work. So
I'm sorry. Sorry, can I have a question to the previous part, maybe?
Yeah.
Did I forget it? Sorry. So if the model of Marek and Glodek is not explaining the frequencies completely correctly, is there any other QPO model which explaining them better, or can you use these techniques to distinguish between different QPO models?
That's an interesting question. I don't think in my knowledge, there is no other model which advocates for this resonant frequency oscillations for 3:2. And no one has tried with a global model with radiation and GR actually in a GRHD model to study the variability. I'm still trying to understand this feature, like why at lower frequency, which is radial epicyclic frequency, the flow is not following radial oscillations, but actually vertical oscillations, which is intriguing. And me and Glodek had spent a lot of time trying to understand that. So it's open question for this.
Okay, thank you. Sorry for interruption.
Yeah. Okay, so I will end my talk with this nice animation that I started to work recently. Probably you have heard that the disk around M87 is not aligned with the black hole spin. So we want to understand the tilted disks around the black holes. And we started to simulate these models. And what we are finding so far that the disk remains tilted for about 4,000 G more C cube. And these are the highest resolution runs ever done. So we are doing it really slow and hopefully compare it with the EHD observations. So I think that's end of my talk. And I will advocate for a strongly magnetized accretion disks for certain black hole accreting systems, not only just black hole X-ray binaries, but also AG and accretion disks, where you have tendency of disks getting gravitationally unstable, like gravitational instability, and not accreting onto the Adhesion, but start to form stars. And to avoid that, if you have strongly magnetized disks, you are making them puffy or elevated, and that would produce some kind of lower density at the disk midplane and not let gravitational instability play the role and form stars and like keep accreting matter onto the black hole. So these strongly magnetized disks are getting more and more important, not only for black hole X-ray binaries, but also AG and accretion disks. I think that's my last slide. Thank you, guys.
Thank you very much, Bhupendra. Yeah, we can clap. So, do you have any questions for Bhupendra? I saw Martin, his camera. Yes.
Okay, so may I speak? Okay, so thank you for a very nice talk. I have a few questions. So first of all, the initial magnetic field configuration has been quadrupole, yes, or some like Deborah was using for this very thin torize.
So in my case, I was not using quadrupole. I was using purely vertical magnetic fields.
So it is like uniform one.
It's a uniform vertical magnetic field, yeah.
Mm-hmm. Okay, and how it develops? So after some time, it will have different structure, and what kind of structure, or it will remain uniform all the time?
Right. So that's this plot showing here. So it starts to form a structure like this in the azimuthally averaged profile. So you have initially vertical magnetic field.
Mm-hmm.
In this case, it's pointing from bottom to top.
Mm-hmm.
In positive G direction. But when the accretion starts to happen, it starts to pinch in the magnetic field, and outflows in the polar region starts to push those magnetic fields outwards. So it creates this bending effect of magnetic fields in the accreting region and bending outwards in outflowing regions. I don't know if that was your question or...
So it will be mostly like monopole, yes? It looks like now monopole, well, split monopole. So one side is coming in
approximately, yeah.
Mm-hmm. Yeah. Okay, so I have another question. So what's the name of the code? It's some kind of harm or a different one?
So this particular simulation was done with Athena++.
Athena. So it is Newtonian code.
It's GR code, but we switched off the GR for this model to keep the focus more towards magnetic effects and reduce the complexity of GR effects. But now I'm following the exactly same model with GR and radiation.
Okay, and may I have another question? So I have found that recently the group around Rezzola released publicly this black hole accretion code. Did you try it, or because there is adaptive mesh, which could be quite useful? So did you try this code or not? Or
I didn't try. Yeah, so that's an interesting question. So this code is called BAC, BHAC. It's exactly similar to Athena++ or Cosmos++. It's another GRMHD code, and I didn't use that because I have been mostly using Cosmos++ and Athena++. But
I'm not sure if they solved the. Sorry.
Yeah.
I'm not sure if this solved the radiation problem. I'm not
That's
sure
right.
if it's
so BHAC doesn't have radiation,
because the adaptive mesh is too complicated for M1, and they were playing around with idea to include the Monte Carlo radiation methods, but I talked with them at some conference, and I think they said that it's too much of a problem.
Yeah, so Athena++ does have adaptive mesh refinement. We didn't need that in this case, actually, because we pretty much knew where to focus most of the resolution. Adaptive mesh refinement is more interesting when you are not able to predict what will happen to the simulation. And in that case, adaptive mesh refinement is more useful. But as you are mentioning that BHAC doesn't have radiation. So, yeah.
Okay, thank you for a question.
Sorry, you are doing the tilted disk of the M87 in Athena with
Athena plus,
because
yeah.
it's not that tilted. Yeah. Okay. So there's a code Andrew Liska, I don't know how to pronounce
Matthew
the
Liska.
name.
Yeah.
Liska, yes. So he's working on his version of HARM with adaptive mesh.
Yeah.
But I'm not sure about if he solved the radiation yet. But
he has not done yet. He's doing based on GPUs. He has not implemented the radiation yet, but I heard somewhere that they are very close to getting done with radiation and probably start to do some simulations.
I heard that though. That too. But it's based on HARM, his code.
Correct, yeah.
I think.
He converted HARM to a GPU-based Hammer code. They called it Hammer.
Yeah. There are many codes and all have some.
Yeah, and it's difficult to master all different codes because, I mean, the basic physics is same, like the source code, like basically most of these codes are based on finite volume methods, same reconstruction schemes and same integration methods. So the base of the code is same, they have just different style of organizing the code.
And every code can do something a little bit different.
Yeah.
There's a nice paper by the HT collaboration, a comparison of different codes. They included 6 or 7.
Yeah, we did that actually just to confirm what different codes show. I did Cosmos ++ part, and BHAC code is also there. And the one thing we found, which I can reveal because I was in the paper, it's very difficult to come up with a steady state mass accretion rate from all these different codes. The m dot is still varying by several orders of magnitude. If you, let's say, compare Athena ++ and Rezola's code or Cosmos ++ or Athena ++, the mass accretion rate varies by many orders of magnitude, even in the steady state. That's puzzling. So that was code comparison outcome, that it's very challenging to come up with a steady state constant m dot.
Okay. So any other questions? No one? So I will maybe go back to the last part of the M87 simulations. What kind of torus you use to initialize it? I mean, it's
so this is using Fishbone Markov model. So my idea initially when I started this project with the student Michelle, who was undergrad student at CU Boulder, now she is PhD student with Mitch. When I started this project, the idea was to understand the different torques acting to align the disk in a strongly magnetized case. So that was in December 2019. And later on, we are also finding that M87 has tilted disks. So now it gave more motivation to complete this project and trying to explain the misalignment from M87. So this is done in Athena ++ with a tilt angle of 10 degrees for now, but the initial magnetic field is purely vertical. So it produces a lot of toroidal magnetic field again. We were expecting that because of strong magnetic field, it will start to align the disk with the black hole spin, which it has not done. So either we need to run it longer or conclude that even strongly magnetized disks are not getting aligned with the black hole spin. And at some point, I can create the spectra from these, so that will be interesting to compare with the HD.
Mm-hmm. Can you have the polarization as well, or not from the?
Yeah, so
can you process it?
Yeah, so there's a complete pipeline ready for that. Athena++ already has that capability that you can read this output from Athena++ and create those images and polarimetric data from Jason Dexter's code and Monica's code. Monica, what is the second name? It's very hard to pronounce. Yeah.
Somehow like that.
Yeah. Right. So Athena++ has that option that you don't need to rewrite entire pipeline by yourself. It has already available Python scripts for that.
That's good. Okay, I'm very interested in this result. It looks good.
Yeah,
okay.
Thank you.
And if there are no other questions, you can just turn on your microphone or raise a hand or anything. Write it in the chat.
Yeah, can I ask one question?
Yes, of course.
What is this m dot and why it's not starting from 0?
Right, so that's a very good question actually. So this is m dot calculated at radius of 5. So initially you do have initial perturbation in the velocity, radial velocity to trigger MRI. That's why it's not starting from 0, but that's a very good point. Yeah. So if we don't perturb the torus, it should have been started from 0.
Okay.
The perturbation was just applied to trigger the MRI quicker rather than waiting for several orbital periods at that radius to let the MRI evolve. But that's a good point. Yeah, it should have started from 0. Yeah.
And what was the magnetic structure here?
So imagine that you have a initial, you go, okay, so if I stop here, the torus here, so what you are seeing on the right-hand side panel is 2D slice, and the magnetic field is going through this torus vertically. So the initial magnetic field is vertical and aligned with the black hole spin. So the magnetic field is not vertical in the frame of torus, but in the frame of black hole spin. So I don't know if you see the cursor of my cursor on the screen. So the magnetic field line is like going vertically like this.
All right, thank you.
Okay, if there are no other questions, I can thank you, Bhupendra, once again.
Thank you, Deborah. Thank you, everyone, for attending.
I hope we'll see you soon in Opava or anywhere else. Have a nice day.
Thank you.
You have the day.
Yeah, looking forward to visit you guys. Thank you.
See you.
Okay, see you soon, hopefully. Goodbye.
Have a nice evening. Bye.
And thank you, everyone, for attending. See you soon. Bye.
Bye.